Welcome to the Joe Cohen Show. Join me as I share my experience with biohacking and invite top health experts to explore the latest technology, supplements, research, and resources for optimizing your body and brain. Hey everyone, I'm really excited about this podcast because I just did an epigenetic test with Tru Diagnostic, and we're going to be going through some of the results, what it means. I'm going to be asking Ryan a bunch of questions. Just to give you a little bit of a background of Ryan, he started a compounding pharmacy called TaylorMade Compounding, became a big company, and he sold that and found Tru Diagnostics. Tru Diagnostics is an epigenetics company, different than a genetics company, just so people understand. Sometimes people get confused. Epigenetics is the gene expression. You have, let's say, genetic predispositions, but then your epigenetics is the gene expression. And in particular, he's looking at gene expression for aging and certain other things, but mainly aging. So there's a test that they provide that's the, Dunedin pace aging scores. So you could see your epigenetic aging and your pace of aging. And they have the largest private epigenetics database in the world with over 25,000 patients tested. And they're doing a lot of interesting work. Now, I have a lot of questions about epigenetics, what my results mean, what's the value of the test. And so I'm really excited to be talking to you, Ryan, today.
Yeah, thanks so much for having me on, Joe. I'm excited to share with you and go over your results.
Awesome. So let's just go through some of the basics. And this is kind of the question that a lot of people have. Where does this kind of epigenetic test fall into the aging biomarkers? Because there's a lot of biomarkers that could be construed as an aging biomarker, including testosterone, blood pressure, basically anything that is correlated with aging.
Mhm.
And so blood pressure, testosterone, even blood sugar. So you get more insulin resistant as you get older. You gain some weight sometimes. So a lot of these kinds of metrics. Where does this epigenetics test fall into the host of markers?
Mhm. Yeah, definitely. And I might be biased, but I would say certainly number one. Probably the
Okay.
most important thing you can do to quantify your aging process. And to take a step back, I think we just want to talk about why this is important. Why should people be even thinking about measuring biological age? And it's this idea that aging is the number one risk factor for every chronic disease and death. So if you don't have another disease, your biggest risk factor for developing one is going to be aging. And if we can treat this process, if we can sort of slow that process down, then we can have massive impacts. So, for instance, if everyone in the world were to be 70 years younger biologically than they are chronologically, we'd be able to cut disease in half, 50% overnight. And so these can make some really, really big changes. But when we talk about all of these different aging biomarkers, you're right. Aging is so complex. There are so many of them. There are blood-based biomarkers. There's VO2 max, grip strength, a whole host of things that change with age. But what we're really doing when we're looking at these aging algorithms is trying to predict which is the most associated with negative aging related outcomes. So what is the most likely to predispose you to disease or all of those other consequences of aging? And by far, the most predictive biological age clocks are DNA methylation clocks. They really explain that variance or those changes which happen with age better than any other clock, which is why they're number one in my book.
Okay. And so let's say, I think the way that we would quantify it, right? Because I think we want to try to quantify these things as much as possible. So, like,
Mhm,
Peter Attia, let's say, is very big into VO2 max because
mhm,
the risk of death from all causes goes up tremendously as your VO2 max is lower, or vice
mhm.
versa as well. Your risk of death goes down as your VO2 max goes up. And so he's very into that. Where does and for good reason, like he gives an example that, if you smoke, your risk of death goes up, let's say 50% over a 10-year period. But even if you smoke, but you have a high VO2 max, your risk of death is still like your VO2 max is actually more predictive than if you're a smoker, significantly more. And
Yeah.
so, what is like, if someone has a higher epigenetic score, aging score, what is the risk of death, and how does that number compare to VO2 max?
Yeah. So to be honest with you, I haven't done a direct comparison with VO2 max. And the only reason for that is because, quite frankly, it's not even at the top of our list in terms of other comparators. A lot of these other epigenetic age clocks are even better than that. And so I give a good example of one of the algorithms we just created with Harvard. It's called Omic Age. So this is an algorithm we've spent over 3.5 years on with Harvard, we basically the most accurate death predictor that's ever been created. It's the only death predictor that can predict death with over a 90% confidence level, 90% accuracy level within 10 years. So basically, if we're trying to predict if you will die in 10 years, we can do it so with right around a 91% accuracy. So we can be fairly accurate. To give you, another comparison, chronological age, for instance, just as a general marker, if we knew you were 80 and then just tried to project, that you're past that average life, we would only be correct right around 75% of the time. So for us to be correct, 91% of the time is a significant improvement. And right now, it's one of the best death predictors that's ever been created, including out of any other markers. But I should also mention that to create that, and with DNA methylation alone, we can also predict things like VO2 max. We can also predict things like grip strength, muscle mass, all with just a few drops of DNA. So we can actually start to inform our algorithms with different pieces of other biology. So, for instance, we can in our algorithm we actually do predict smoking status, and some of the best things we also predict are lung function measurements, not as similar to VO2, but things like FEV1 or FVC, these lung function measurements, which when we incorporate smoking and these lung function measurements, and even other markers like triglycerides, HbA1c, all through DNA methylation, we can get a really big picture of the biology of aging. And that is the most informative to us. And this is really important because as you and I were both talking about, aging is complex, right? There are a million different biomarkers. There are a million different things that change as we get older. And so we really want to capture that full constellation of symptoms and different problems so that we can really predict the outcomes, because that's really what we want to change is what are our risk factors and how do we actually use this data to make ourselves healthier.
Okay, so that's interesting. I mean, bottom line is you're saying that this is more predictive than VO2 max based
Yeah.
on the data you've seen.
Definitely. And by a wide margin. And so we're not talking, 10%, we're talking more like 20% increases in prediction of most age-related disease. The other thing is that generally VO2 max might be predictive of things like all-cause mortality, but might not be as predictive for things like depression or, type 2 diabetes or whatever, kidney dysfunction, right?
Right.
So it might have certain aspects of aging, but it's not the whole thing. And it might be very, very good because generally, those correlations between physical function are really important for determination of overall health.
Okay. So, do you mind if I ask you, and what is your biological age with this test?
Yeah. So, to be honest with you, I started high. I started when we first did the company. I was expecting to do pretty well, but I was about 3.5 years older,
Wow.
biologically than I was chronologically. Now I'm thankfully around 2 years younger, so I'm right around in my 29.5 age group, and at least biologically. And I keep seeing some improvements, but I also do see things that make me a little bit worse. My rate of aging, which is one of our favorite algorithms, I struggle with that a little bit sometimes. My rate of aging goes a little bit higher than most people. On average, I'm around a 0.83, where other people are setting, records at 0.69 or even 0.59 is what I've seen recently. So my rate of aging is not as great, but my overall biological age is certainly getting better.
So that's something that I'm a little, confused about because let's say for me, right? My biological age is around what my actual age is.
Mhm.
Okay. But my rate of aging is 0.72. So if that's the case, and you can say that, okay, but maybe I brought it down recently, that could be the answer. But if that's the case, I feel like my age should be lower. And like you're saying that you actually brought your biological age down from 3 years older to 2 years younger. That's a 5 year difference, but your rate of aging is actually higher than mine. Mine is 0.72.
Yeah.
And so how does that make sense?
Yeah, and unfortunately, this can get complicated very, very quickly. But the important thing to note is, and really to draw maybe an analogy to genetics. I like to talk about the difference between polymorphisms in genetics and epigenetic or methylation or genetic risk scores, right? These polygenic risk scores. Whereas, if we're looking at a certain gene variant, we can find out what that means, what that tells us. But when we incorporate it into maybe polygenic risk scores, we're looking at multiple different SNPs. What we're essentially doing is combining a lot of pieces of data for one overall outcome. What is your risk of X, right? And in the methylation
Which is
space,
what we do. Yeah.
exactly, exactly.
Yeah.
And in the methylation space, um, almost everything that we can read out is not going to be polymorphism based. It's all algorithm or risk based. So when we talk about these algorithms or these outputs, we really have to talk about the method for reporting the algorithm. So whenever we're talking about each of these different results, we're talking about a certain different algorithm, a certain different way to interpret that data. And so sometimes they're not all compatible because they've all been trained or created in different ways. So one of my examples of this is when these clocks started, these clocks were really just meant to predict your chronological age. So they were used in things like dating refugees to see if they were adults or minors. They were used in crime scene investigations to see if how old someone was if they left their DNA at a crime scene. But they weren't really used as a health tool until they started to see this trend, which was that those people who did this testing and were younger than their chronological age were protected against negative outcomes in the future. And then vice versa, those people who were older had higher risk. And so even though this was meant to be something to predict your chronological age, because of these health associations, we found out it was really a biological age predictor. But the problem with this is that the better that those algorithms got, the closer they just got to telling you your chronological age, which for most people, you don't need an expensive test to tell you, right?
Right.
You and so those are the first generation clocks around 2013. But people really quickly realized that if we really want to capture the biology of aging, we've got to have better ways to train these algorithms. And so the second generation of clocks started to be trained to different things. Things like 9 blood-based biomarkers like albumin or different hormone levels that change with age, or predicting time until death, or even trying to predict telomeres as an output. And those clocks got better. And the reason we know they got better is because if someone was 1 year accelerated compared in this clock versus the old clock, this clock predicted much, much more risk. And so we know that it was capturing more of that biology because it was able to be more predictive of negative outcomes. And then the third generation, which is the Dunedin pace, is the only third generation clock, that one that tells you your pace of aging. And so that's why it's one of our favorites. It's definitely the most updated. Came out in 2021, and that actually tracked patients longitudinally. So it tracked patients from the moment they were born all the way until they were, age 45, to sort of establish this pace. And so when we talk about some of these early biological age clocks, we might not like them or have a preference over them as much as some of the newer ones, like that Dunedin pace, which is why that Dunedin pace is always the one that we're going to trust more than any other. Another good example of how this can sometimes cause some issues is whenever we talk about interventional trials, right? The real reason people want to measure this is so they can change it. And I always like to talk about caloric restriction. Caloric restriction is one of the most well validated anti-aging therapies across multiple animal species, including humans. But if we look at those first generation clocks, as one trains to predict chronological age, um, they actually go up with caloric restriction, which we know is not correct. So basically these clocks that have been trained to predict chronological age, they're capturing some aging related biology, but really what they're capturing is biology changes that are correlated to chronological age. And that's not nearly as important as the actual physiological changes which are happening with our body as we're aging, where like the Dunedin pace can pick that up because it was trained on lung function measurements, as we've already talked about, HbA1c, even gum health measurements from dental imaging. And together, that's able to capture a lot more biology. So whenever we look at that clock in caloric restriction, we see that it significantly goes down, just as we would expect. And so some of these earlier clocks have certainly had limitation. And now these newer clocks that are coming out are the best ways to quantify aging biology and the most predictive. I'll give you one more stat just to illustrate this difference. One standard deviation increase in the Horvath clock, the original Horvath clock that came out in 2013, would lead to a 2% increased risk of mortality versus one standard deviation increase in that Dunedin pace. That would represent a 64% increase in mortality.
Oh,
So
wow.
again, as we're comparing which one's more important, we're really not going to care about that 2% as nearly as much as we're going to care about that
What
64%.
what would that, standard deviation be equivalent into, like, raw score metrics? Like, point
Yeah.
how
So
many points?
Yeah, so generally, it's gonna be right around point, I would say 1.9 points on that scale.
Okay.
That's still a big margin, right? In terms of one standard deviation. But again, it plays a major impact, 64% increased risk of mortality, but it also has effects on every quality of life related thing too. Which is the other reason we really like that Dunedin pace is because it is related to things like facial aging. It's related to memory and IQ, mental processing speeds, balance, grip strength, and muscle mass. And
Interesting.
so that's the other reason we really like it is because a lot of people often say, "Why would I want to live longer? Why would I want to live in a nursing home and have a poor quality of life?" And we like to show that it's not a that's a sort of a false dichotomy. You don't have to choose between a long life or a healthy one. If you're improving your aging, you're generally going to be improving all of your quality of life, how you look, feel, and move about the world, while still having longer life as well.
That's very interesting. So that clarifies. I actually completely understand it, like what you said, in the sense of, first of all, they're really different algorithms, one and the other, and they're predicting different things a little bit, right? So the
Absolutely.
first generation, like you said, is really just trying to predict your age, not how healthy you are, your actual
Mhm.
age. The
Yeah.
second generation is still gonna be heavily skewed to predicting your age, your actual age. And so even if you're super healthy and you're very low risk for disease, it might still just put you at your actual age just because there's a lot of weighting to things that are your actual age. The real the real good marker that you guys are offering is the pace of aging, which will go up and down based on, and that's where that you're seeing the big differences in mortality.
Yeah.
So that is really interesting. That's the thing that we really need to look for more than what my actual biological age is, I feel like. It's
You're
it,
you're
yeah.
absolutely right. And I want to mention that the restrictions of some of those early clocks are being improved and changed. So this new algorithm we have coming out with Harvard Omic Age, which we've been again working on diligently, that is actually even now more predictive than just needing pace. And we also created an algorithm with Yale called Systems Age, which can actually break down the age of 11 different organ systems, and then tell you which organ system is aging fast. Between the Dunedin pace, the omic age, and our systems age clock, we have the best aging predictions for any disease. And so that includes neurocognitive things like Alzheimer's and Parkinson's. It includes heart disease, it includes cardiovascular disease, renal disease. We have the most predictive algorithm to quantify aging in every single disease outset between those three. So with that being said, we really feel like now we can capture the age with resolution we've never seen before, but also give now the amount of information we need to really know what to do to change it. And that's also been something that's even on your report, you know we hadn't been able to do. We might be able to tell you if you're accelerated or if you're decelerated, which is a great start to know where you're at. But we weren't able to make personalized recommendations or tell you what's driving that process in you. And now we're getting to have that resolution.
Oh, that would be amazing if you can actually have recommendations based on it, because the way I see it, the biggest so first of all, I'm a very big fan of any kind of tests that will measure health, right? Because no matter how good the test is, there's always going to be a weakness to every test and a strength to a test, right? And so we have a lot of lab markers that I study a lot of lab markers that increase mortality quite a lot, right? Like
Mhm,
60, we're also seeing, like, you could do a lot of markers that are like 64% increased
mhm,
mortality if you have this, that, and the other. So I look at a lot of lab markers, and the way I see that, alternative medicine, functional medicine, and medicine ideally as well, but that's gonna take a long time. The way that that needs to go is really the data. Like, what does the data say? I don't care about your opinion, what you
mhm,
think, what does the data, let's just look at facts and then come to conclusions based on facts. And so that's what testing does, is it's data, and it's a fact that if you get this pace of aging, your risk of all these different diseases is lower by this amount, right?
mhm,
Um, as on a whole, right? Not on an individual level, you don't know exactly, but that's what I really love. I love because right now in health, it's like this diet, and I've got this diet, and you should do this, take this supplement. I don't care what anybody says anymore. Show me the data. You did this, and what happened, right? Like,
exactly.
what biomarkers did you optimize by doing this? I feel like we wanna move this as much to, actually, like, data oriented. And that's also what we're trying to do with self decode. When we tell you your polygenic risk, you can then say, okay, here's my weaknesses, genetic weaknesses, and then what are the database of clinical trials that counteract all these weaknesses, right? And then something
Absolutely.
that, and that's like a starting point, and then something where your test comes in, and other kinds of lab tests is you can see, okay, I'm doing this now. I want to make sure that X, Y, and Z are also good based on what I'm doing, right?
Yeah. Yeah.
And
You're
so
exactly,
that's
yeah.
yeah. Sorry.
Sorry, didn't mean to interrupt, but I couldn't agree more. I think that this is sort of the thesis of really why we're so excited to create age biomarkers is because we know that aging is so important. But if you ask any physician, any person what they should do to protect their aging, you might get literally 100 of the different answers. It's always going to be different. So we really wanted to standardize this process and make aging research sort of just consistent across the board, where we have the same biomarkers that we can, if we're measuring the difference between hyperbaric oxygen at high pressures or low pressures, we have data to tell us which direction is it's really driving. And we think that again for longevity, this is something that's been a long time coming. Because I think that everyone realizes that they probably know people in their 50s who look like they're 70, and they probably know people in their 70s who look
Right.
like they're 50. And that means something to us if we see someone who's doing all of these things, but underlying all of that is all of the biological changes that make someone healthy. And we're really trying to quantify that to make aging a real science, to make it a part of medicine, just as, cardiovascular disease is a real part of medicine. We
I
really
love
want to
that.
make it a
Yeah.
specialty we can measure. And you're absolutely right. Without a consistent measuring stick, it becomes complicated and gibberish really quickly, where all the noise just confuses you instead of empowers you.
I love that. I'm gonna ask you a question that is impossible to answer really, but I'm curious what you think. If 2 individuals will take the same thing, right?
Mhm.
The same supplement or do the same thing, are I'm assuming like this and every other test, people can have different responses to different things. So, like, in one individual, maybe a vegetarian diet decreases their rate of aging, let's say, and maybe in someone else it doesn't. Do you see that, or not really? It's pretty
I would,
consistent. You
yeah.
do this and it works for everybody.
Yeah, I would say that that we do see it. We do see differential responses. However, it tends to be relatively uncommon. I would say that a lot of people have very similar responses, but I will also mention that that's probably a limitation of our patient population as well. Where the people that are doing our testing tend to be some of the healthiest, generally a little bit more affluent and well off. And so as a result, we have a very healthy cohort that is really not very complicated at the end of the day. But whenever we start getting into people with complications, people that maybe have comorbidities like different types of diseases or cancer, then I think the answer is yes. These things start to change in really large ways.
I, I
Actually, to
assume
go
you
to
don't have a lot of smokers as customers.
Not many, not many. But one of the cool things about, and this is a little bit of a tangent, but we actually have an algorithm that can tell you how much you've smoked across your lifetime in terms of pack years. And that
Oh,
algorithm
interesting.
actually is more predictive of negative smoking related outcomes than even self-reported smoking status. And
Okay.
so we have some cool ways to see behaviors even in that DNA methylation. So we can actually tell you about our cohort behaviors. But to go back to your example, we actually just did a trial with twins between vegan versus omnivore diets. And so we did this with Stanford. Many people might have seen the Netflix documentary Game Changers, which was about this sort of vegan diets. And they sort of financed Stanford to do another study where we took 22 pairs of twins. So we actually took one twin on an omnivore diet. We took one twin on a vegan diet for 8 weeks. And measured their responsiveness. And this trial was really, really good for us because we had twin controls, right? We eliminated genetic differences, which is a huge part of this analysis. And when we did, we saw much more consistent results. But whenever we compared twins individually, we did see differential responses, according to which suggests to us that we might have different responses based on our underlying genomic factors, right? Which is probably not a surprise, but it's an important thing to mention. And I won't bury the lead anymore, but we did see anti-aging effects with the vegan diet versus the omnivore diet. It was just in 8 weeks, and it was in a younger population. It's a couple things that I think are really important to tell there, but yes, differential responses, which is exactly why we think people should get an idea of what's driving that, and then remeasure to see what's actually working for them versus what is the general recommendations for a population size cohort.
Yeah, I mean, that's a very interesting one. I think the critical factor for the vegan diet study that you did was 8 weeks. And, some of the main problems with the vegan diet are actually long term, in my opinion, right? So,
Yeah. Mhm.
I've seen many people build up. I study food sensitivities a lot, and I see people build up food sensitivities on a vegan diet because mechanistically, they're deficient on a lot of things that counteract that. And so that
Mhm.
takes actually time to occur. Whereas if you're on a vegan diet for 8 weeks or maybe even a half a year, you can see good benefits, but you would really need to see a very long-term trial. So like multi-year, like 5 years, I would want to see in order to
Yeah.
really get information from
Yeah. We couldn't agree more. I think that it's a good start for data generation, but we certainly would want to go longer, especially and one of the biggest considerations for us is frailty and muscle mass. As we get older and start to become sarcopenic, lose that muscle mass. Um, Sometimes some of the biggest critiques of the vegan diet, they don't have enough protein to maintain muscle mass. And that's the other reason I mentioned our cohort was relatively younger. Is
it.
because they're probably not experiencing as much muscle mass as maybe some older people who are undergoing that frailty process. And so with all of these studies, you have to take all of that into consideration when you're doing these analysis. But hopefully they're still generating some good data and answering some questions. Like for instance, I think that differential response due to maybe other things that we saw here.
Okay, so here's a quick question. When somebody looks at these scores, are you doing like, okay, so my pace of aging is 0.72. That's what my result was. Is that compared to the database of people that you're testing? Because you're testing a very healthy population, or or is that compared to just the general population, which is mostly sick,
Yeah.
in my opinion?
Yeah, another great question. Another great question because unfortunately, every algorithm is going to be different according to the population which created that algorithm.
Correct.
So, for instance, if we go to a European population and create an algorithm, it might not hold out in terms of validation of performance in a U.S. patient population. We've actually had this happen. We had an obesity risk predictor that we created in a Spanish population that just didn't work, quite frankly, in the U.S. population. But in the case of most of these aging algorithms, we can improve that because of the size and the sample cohorts we've used to generate the algorithms. But this is so, for instance, we can generate this cohort, but we still have to validate and test it in a completely separate cohort. And so, for all of our testing on our reports, none of those patients that we've used in our data sets have been used to train any of our algorithms. So we
Mm,
try and keep it separate so that we're not creating an
skewing
algorithm
the data
on
set.
on a
Yeah.
cohort that it's not applicable in. And but this is the other thing that I think is the most important. And that is that for anyone who's doing a biological age test, the number one recommendation for anyone doing that is find one that has been published, because this is how we actually know that the algorithm works and that you should pay attention to it. Otherwise, I tell people it's like going to a fortune teller. You can choose to believe them, but it's better to have some of that data.
The
And so,
the
number
funny
one of which you need to publish.
The funny thing is, like, everything you're saying, I'm like, "Oh, this is like deja vu within my company." Meaning, like, you have to train it on this data set, and then it might not work with different ancestries, which is why we do an ancestry-adjusted polygenic risk scoring, and also be extremely careful with genetic companies because basically what's happening is anybody just pops up, goes online, looks at a couple snips, and says, "Oh, here's your risk for this," and there's no data whatsoever. They're just pulling together a bunch of stuff from their ass, and we're
Exactly.
just like, "What?" Like, that's not predictive of anything, and that's why we're also we're about to publish all of our stuff. Like, we have
Yeah.
internal data right now, but the key thing is, like, we're about to publish all this stuff to show everybody, okay, here's what the algorithm could do. And that's what I really like about you guys. You're not just saying, hey, just trust us, like we're the best. You're actually publishing stuff. And I hear based on how you're talking, based on the way you're actually doing things, it's not just based on to be very honest, a lot of the ways that some of the functional medicine world works, especially in
Yeah.
genetics. I don't know if it's like this in epigenetics, but in genetics, it's just like everybody and their grandmother is creating, here's a bunch of SNPs, and I'm going to tell you everything you ever wanted to know from these 3 SNPs or 5 SNPs or 10 SNPs. It's like, no, that's not how it works. There's like millions and millions of SNPs that are
Yeah.
interacting with these diseases, and you have to train models, right? You have to use very sophisticated systems, machine learning, AI. You can't just have somebody go to PubMed and type in some SNP RSIDs and here's your risk.
Yeah.
It's useless.
Yeah, you're 100% right. I think that, and I hate to say this, I mean, I've seen this in genetics, just like you're mentioning. That's why there's, a million different companies out there, but very few doing it in a reliable way. Which I also think is why some people get disillusioned, not just with, genetics, but epigenetics as well as, for instance, even on our testing, some people might say, hey, I took a biological age test. I did everything the right way, and then my age shot up, right? And caloric restriction is a good example, right? We talked about that with those first generation clocks. Uh, and they get disillusioned saying, "Hey, this technology doesn't work. I know it doesn't work because I lost 20 pounds. I decreased my LDL cholesterol. My systemic inflammation went down, and my age still went up. What's happening here?" And you can disillusion people very quickly by not having algorithms that are accurate. And it's exactly the same way I think that people think about this idea of aging. It's not recognized as a disease by the FDA yet. And so it allows them to do things a little bit without regulation. And I think that that's exactly what's hurting the space is it's taking this concept of age and making it not scientific and just more of a novelty. And I think that we really want to do it the other way. So yes, publications, I think you're the exact same way. Look at how that data reflects. And it's not hard to judge these things. You can have an equal measuring stick. A lot of these populations have all of the same data. So they have genetics, they have epigenetics, and you can compare them side by side to see what one works better.
And you find that there's a lot of just crap. Like I haven't seen as many of these like mom and pop just marketing scams as I
Yeah.
see. Like every day there's a new genetics company out there. Like, hey, what do you think of it? Somebody literally just sent me yesterday. Hey, somebody told me to get this test. I look at it. They're looking at 5 SNPs here, 10 SNPs here. I'm like, I could see this is already junk. Like there's no validation, no real
Yeah.
science. I could build this in like literally a week. Just
Yeah.
grab some
Yeah.
snips from PubMed and chuck them in there. That's
Yeah,
really what it is.
you're exactly right. It is happening, unfortunately, in methylation, and one of the other yeah, so it's certainly a problem. But with methylation, I hate to say it, it's even more complicated than genetics, which leads to many more problems a lot of the times. So one of the things is obviously it changes, and it also changes from cell to cell. So the reason I explain this is every cell in our DNA has every cell in our body has the same DNA, right? If we look at our heart or our liver or our brain, same DNA sequence, but massively different epigenetic sequence. That's because our heart needs to behave like a heart. So it's going to turn off some genes and turn on other genes, whereas our liver doesn't need those same. It's going to have a different expression. And so even for us, tissue type matters. What tissue we're actually measuring, saliva versus buccal cells versus, blood. We only use blood because for us, that's the only data that has validation. So people have been banking blood and plasma for 50, 60 years. We can actually look at those markers and then see what happens to them. So that's actually how we know that our predictions on death are accurate, because we've actually seen people whose DNA we've measured and then predicted when they're going to die, and then actually have that real data to show when they actually did die. But no one really has kept, I would say, banks of saliva DNA because usually blood DNA is they already have, and so it's really hard to validate these long-term things with saliva. But it also brings up problems of what we're measuring, right? We might take my blood and we might take your blood, and you might have many more CD8 T cells than I do, or B cells than I do.
Right.
And that can affect these algorithms if you don't control for it. And so in the early days, we didn't control for it. We didn't take into account immune cell subsets. And what we saw was that people sometimes who had massively increased ages or massively decreased ages, which we know is not
Mm,
real because,
right.
having a sickness doesn't mean that you're going to die, 20 years earlier. It means that at the moment you're just slightly different, right? And
Right.
then you're going to go back to normal. And so we have to control for what cell types we even see within a sample. So whenever we do a sample now, we actually control for 12 different immune types. We tell you what your CD4, your naive, memory cells, your B cells, natural killer cells. We quantify those so that we can make sure that if one of those is increased, we're not changing your algorithm. And so cell type is important, precision is important, and really epigenetics is where DNA was 20 years ago. It's still got a long way to go. It's got a long way to grow.
100%.
And we're really trying to make sure that that it's all consistent and reliable, and actually makes a difference. And this is one of the big reasons we haven't gone direct to consumer in as big of a way and really talk with a lot of providers, because you need a lot of bigger medical knowledge to make sure these are interpreted in the right way, or at least you have. Now we're getting to a place
Yeah.
where these are N of one use case scenarios and a little bit more help.
We're seeing it actually is quite complex in genetics in different ways as well, and
Mhm,
you see sometimes people don't know how to interpret the results. Like,
mhm,
you can like, there's certain basic things, for example, you can be high risk for a disease, but low actual risk, like high genetic
mhm.
risk, low actual risk, because it could be very lifestyle based, right? You could have a high risk for blood pressure, but if you're actually doing all the stuff that you need to be very healthy, it's not likely you're going to have a high blood pressure if you're just being really healthy, you know? So, at least not at a age of 40, 50, whatever, maybe at like 90 or something. But the point
Exactly.
is that there's a lot of these kind of complexities, and also people don't understand probability very much. So, these are all markers like for to predict, but technically you could have a good marker and then you could die tomorrow for something that it just didn't pick up, right? It's always
Yeah,
possible. So
definitely.
that's why
And
I think you really want to get as many data points as possible. But like you said, I think the epigenetic age is a really good data point that
mhm,
you can track that you're not going to get from your doctor, like
yeah.
from a CBC or something like that, right?
Exactly. And I think that's one of the other things I'll say about, methylation is that it is able to do some unique things because it's also measuring current status, right? Because of some of these changes. So, I already talked about how we can predict, your smoking and drinking behaviors. We can go ahead and tell you, even things now, we can diagnose schizophrenia, things like
Oh
schizophrenia were
wow,
previously, yeah, they were only diagnosed, could be made in an office from a psychiatrist. Now we have a molecular signature. This is what that process looks like. And so, we can do a lot of really cool things, from everywhere from predicting what zip code you've lived in most of your life due to pollution markers in your DNA,
wow.
to telling you, with high accuracy what all of your blood-based biomarkers are, based on patterns we found. And so this technology is growing. It has limitation, but also has
Did
some features. And so I think together, the better, more data, the more you combine it, the more you'll learn.
did you hear of that guy that made the rounds on social media about he can predict the exact day you're gonna die? uh
I've seen that, but
Without
I
any data, of course.
yeah,
You
it's
guys are spending like we're both spending like tons of money
yeah,
like creating like legit products. He's like, "Yeah, I'm a human biologist. I can predict the exact date you're gonna die based on, 10, 20 biomarkers,
yeah.
blood markers or whatever." No, that's just not
Yeah,
possible for any test. Like no matter
no.
how it's just not possible, right? Like
Yeah, not at all. I actually, tried to reach out and contact him, about this because I was like, "This is an amazing breakthrough. Just show me." And I'm on board. Um, and I never heard back, but yeah, no, I think that whenever we create our death prediction models, again, 90% accuracy in 10 years is really good. It's better than anything else that's been created before, but we will never claim to have a resolution to tell you the day or even close to the month of when you might pass
right.
away. That
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 would be
is,
impossible. That's
wild. Yeah.
impossible. Yeah.
Yeah, and
I
and
mean,
and
even
so
if you predicted a month, it would be probabilistic anyway, right? So it would be like,
certainly.
okay, according to this probability, but that means that, it would just, yeah, there's no way, like, it just can't
Yeah.
happen. Yeah.
Exactly. And even, again, we're getting okay with these predictions, but that level of resolution is just absolutely wild. Insane. But, I bring it back to even our chronological age prediction. Whenever we first did this, we had the mean absolute error was around 5 years or so. So basically, we could predict your chronological age within a plus or minus of 5 years. Now, just, 2 years later, we can predict it with a margin of error of 1.2 years, which is really, really good. But we're starting to see it sort of maximize out, right? It's not going to get much better at this point. That's really our margin of error because it's just this intrinsic biology changes that happen on individual to individual. So I would always be skeptical if claims sounds too good to be true. But another reason, again, to drive back to see the published study. You can believe it
Right.
if it's been peer
100%.
reviewed.
We're on the same page. I so I would actually there is a published I wanna talk about, this published study on, like there was this researcher, Morgan Levin, I believe his name was.
Yeah, yeah,
He
yeah,
did a
yeah.
published study on 10 lab tests and predicting the biological age for that, and there's some companies that use it.
Mhm.
Um, I'm assuming, it's gonna be it's obviously different than what you're doing. They're using actual lab tests and then saying, "Okay, people who had these levels at this age, this is their
Yeah,
risk," and they're trying to correlate it with some lab tests. How does that
yeah.
compare? It's a completely different test, just so people are understand, but how does that accuracy compare to the, true age epigenetic test?
Yeah, so the answer is that the true age is more predictive as a standalone. But I love to talk about this because so Morgan Levine, you're absolutely right. Her history is actually in this epigenetic space, and she's probably one of the most exciting epigenetic researchers in this space. Definitely an idol of mine. She started actually with Steve Horvath, who was the creator of these first clocks as a postdoc. Then she went to Yale, and in that process of her postdoc, created this algorithm you're mentioning, where she uses 9 blood-based biomarkers and then also chronological age as a feature to predict biological age. And she created first the score from just the blood-based biomarkers, but then she actually trained DNA methylation to predict that score that she got from the biomarkers. And so, whenever we can talk about this, we can talk about both. One is a blood-based algorithm, the other one is a methylation-based algorithm, but they're based on that same data set. And so we actually, in our Omicage publication, have showed that we actually created a 17 blood-based biomarker that's around 17 times more predictive, or sorry, 17% more predictive
Oh,
than PhenoAge. So it uses a few more markers, but we trained it in a much larger group. PhenoAge was trained in around 2,000 individuals. We trained ours in 60,000 individuals. We started with 61 biomarkers in blood, narrowed it down to 17 to create the most predictive algorithm, and it's 17 more percent more predictive. So it goes to show you two things. I think one is that you can still create amazing biomarkers of age prediction with just blood-based markers. But again, the more resolution, the more data points you can include into a model, the better your prediction gets. And that's again just because aging is so complex and so different and variable in everyone. And so I love that algorithm PhenoAge. I think that for people who have blood and don't want to spend any more on testing, it's a really good point in the right direction. But it's not nearly as predictive as even our new blood-based markers, and then those even are not nearly as good as our DNA methylation versions of those blood markers. And the reason for that is because DNA methylation, we measure around 1 million locations in the DNA, which is still a fraction of the total we could measure. It's 29 million per cell. But even with those million, we can capture elements of biology that can't be captured from single blood-based biomarkers. So by using DNA methylation, we can in that large data set, all those different things we're measuring, we can start to include things about all these different organ systems, your neurological function, your kidneys, your heart, your brain, your glycosylated improxenescence. All of these things can be featured into a more robust biomarker that's capturing a little bit of other different things. And so that's where sometimes the reason that we like DNA methylation is because like genetics, you have the benefit of scale. You have the benefit of so many different markers that can tell you a little something. And even if it's only the fraction of bit of information, it still improves the overall prediction. So I love PhenoAge. PhenoAge is limited a little bit as well because it does use chronological age, which we found that
mhm.
as people start to use chronological age, they're sort of biasing their algorithm already in the first place. And so the newest algorithms don't incorporate age as a factor. They want to just look at the biology and let that speak for itself. But it was definitely a good start. And actually, it was really the first ever of those second generation clocks that we mentioned. Those ones trained to not just to chronological age, but to other factors of aging.
Okay, so the bottom line is I would say that you think there's validity and use to it, but you think that the, true age, this Dunen pace, incorporates more factors and is more predictive. What it comes down
Oh,
to.
definitively. We in the Dunedin PACE, we used instead of 9, we used 21 blood-related biomarkers, and we tracked it longitudinally in the same patients. And so for that reason, that was better. In our omic age, we used tens of thousands of data points from clinical biomarkers, metabolomics, proteomics, and that's capturing an even bigger amount of biology. So I think you're exactly right. To sum it up, I think it has utility. I think that for people who don't want to spend more on testing, it's a good place to start, but it's not the most predictive, but it's still showing trends and can be informative.
Is it gonna be different? Like I would assume that the prediction is gonna be somewhat different, meaning like so what you're saying TruAge is doing, just doing it in pace, is incorporating many, many biomarkers. But the more biomarkers you incorporate, the more you're de-emphasizing individual biomarkers, in a certain
Yeah.
way. So, for example, let's say you're taking into account blood pressure, but that means that you could have still a high blood pressure and a good rate of aging, right? Because it's not
Mhm.
heavily focused on one area. So what you're doing is you're trying to take as broad of a metric as possible, but that still means that these individual metrics could still be useful
Mhm.
in various contexts.
Yeah, just I think a good example is let's look at HbA1c, right? HbA1c might be the most important marker for predicting diabetes, but it might not be the most important marker for neurodegenerative disease, or it might not be the most important marker for
Right.
physical function. And so, what we are doing when we're doing these algorithms, we're saying, "Hey, computer, basically take all of these different data points and let us know what is the most important for different types of outcomes. And for most of the age outcomes, we do choose a surrogate marker of death as a really good predictive marker. But we can also do it in other ways where we're waiting for different diseases, and that's where this is going eventually. Is much like
So that's yeah,
yeah,
that's a really critical point though. What you're doing is your main metric is dying, right?
mm,
However, you're not like necessarily taking into account, let's say, an individual who has a very high risk in a very specific area, and then they end up dying from that specific cause, right? So, like,
yeah,
let's say somebody has a high risk for Alzheimer's or cardiovascular disease, and then they just end up dying from that, even though they might be doing a whole bunch of other things that are
yeah.
predictive of good health. Um,
Yeah. Yep,
right.
you're exactly right. Yeah, and that is so that is, again, why at the end of the day, one of the things that's so hard is to define aging. And sometimes you get into this circular death loop, of saying, "What is what is aging?" I think most people could, see it, and identify it, but couldn't thoroughly describe it. And, I always like, and again, when we first started this, there were 9 hallmarks of aging. Now there's 15, right? And so this is a moving concept, but the one thing we know about aging is it predicates and predisposes you to all other aging conditions. And so there are algorithms which train for time until death versus there are algorithms which train for comorbidities. There are algorithms which, say, try and get more close to a health span metric than a lifespan metric. And so that's why, again, whenever you're learning how to interpret these reports, you really have to learn the algorithm. And this is why validation is so important, because that's where you find out this algorithm's tendencies. Is it good at predicting this, or is
Are
it good at
you
predicting this?
so did you train it for health span or lifespan or both?
So in the case of our omic age algorithm, we train that for lifespan. But that Dunedin pace marker is some of the most predictive of comorbidities and quality of life because it wasn't trained for lifespan. It was trained really on pace of aging change, so negative change in these biomarkers from optimal.
Mhm.
And so again, that's why it generally performs so well. It's so predictive of these disease outcomes. And our omic age is so predictive of death, for instance. And in the case of the systems age clock we're coming out with Yale, we actually train biomarkers for each organ system. So, for instance, we took liver specific biomarkers and looked at how those change over age to create this liver age, and then same with the lung or the kidneys, and that again gives us more resolution.
So I think people would want like a big picture, like how do I integrate all this stuff? Because there's a lot of things that people could be doing,
Yeah.
right? And the way I see it, and you can tell me what you think. The way I see it is you want to prevent the things that you have right now, like you're dealing with some issue now, you want to solve that ideally, right?
Hmm.
Especially if it's something that will lead to some kind of problem. So if you have like brain fog now, your risk of Alzheimer's is probably going to go up,
Yeah.
right? Or some kind of neurodegenerative disease if you have if your brain's not working at the age of like 30 or whatever, right?
Mhm.
So if you have an issue, I feel like that is like probably the most important thing you want to resolve. Then like longer term, you want to not you want to prevent big
Mhm.
diseases, right? So there's like that for that's what genetics you could see, okay, what are my predispositions for different things? What should I prevent? And so you want to yeah, so that's kind of like the base and so something like what we do is we match up a database of clinical trials for different things that you could do.
Mhm.
Then you wanna test. So you might have a higher genetic risk for whatever, let's say cardiovascular disease. You wanna actually test all the known biomarkers that are causally related to cardiovascular disease, and there's quite a lot of them, right? So that's
Mhm.
how you test those biomarkers in order to and you can move, almost every biomarker that blood test, I feel like you can move. I've moved them,
Mhm.
right? So
Yeah, certainly.
you want to move them in the right direction. And then where this comes in is you also want to see, okay, in some way your focus should be like a little narrow in a certain way because you want to take care of your issues. You want to prevent certain things that you might be high risk for. But on the other hand, you also want to see, okay, the totality of everything I'm doing, right?
Mhm.
Is that working for me or not, right? And so that is what it's more of a totality. I wouldn't like make huge changes based on that. But the thing is that if that totality is bad, or like, hey, I'm aging at a regular pace, that means that you probably should be doing something different to bring that down,
Yeah.
right?
Definitely. And I think that's where we're at now is that if you have a disease or you have a health problem, treat that first, right? But
Right.
what we're saying with aging is that for people who are, healthy and are looking to we know that preventive medicine is the best medicine, preventing disease before it occurs. And aging is just the biggest risk factor every chronic disease for a reason. It's progressive loss of function. And so for anyone who is healthy or is recently, overcoming some other type of health condition and now saying, what else can I do? This is really that perfect marker because if you're addressing it, you're addressing the largest part of your risk. And not even by a wide margin. If we look at relative risk for the top three causes of death, we see that age is around 45% of the relative risk versus even smoking and obesity, which is like 5 to 7%. Right. So as we consider, just how impactful aging as a biomarker is, this is really, really important and should certainly be quantified. But in the future, DNA methylation will also be used to talk about disease status. So one of my favorite papers is that they can actually now not just diagnose types of diabetes with DNA methylation, they can actually tell you what subtype you have, each with different recommendations for treatment and each with different risks. One person might have peripheral neuropathy as a problem. Other people might have other issues like spots in their eyes, for instance. And we can actually now predict which subtype of diabetes you have to then make better recommendations. So DNA methylation as a biomarker is certainly growing to clinical use, but right now I would say it's most applicable in an aging framework.
Okay. And so how does MTHFR relate to these things? Because I mean, I have both of the bad variants, two of them,
Yeah.
so I'm homozygous for those negative variants. How does that affect the pace of aging? Do you know research on that?
Yeah, so certainly, and one thing I want to mention is that a lot of people get this idea confused. When we talk about DNA methylation, a lot of people think about these MTHFR SNPs or COMT SNPs, and we're measuring different things, right? So if someone asks you about your ability to methylate, that is where you might want to get a genetic test. But if they're asking you about what is your status of DNA methylation, so what DNA is turned on and turned off, that's more of what we're looking at. But as you mentioned, they are related to some degree. What we know, for instance, is that women who have the MTHFR 677CC variant can improve their epigenetic age by about half a year in just a few weeks, just by supplementing with things like methylfolate or folic acid or methylcobalamin. But really in all the other instances of this, particularly even for men, we didn't find much of a difference. But for women with the MTHFR 677CC variant, we do recommend supplementation. And by doing that, you'll probably have a change in your epigenetic age relatively quickly and in a relatively big fashion.
Interesting. And so I want to, let's say, retest again. And so how long do I need to wait in order for it to essentially reset? So like HbA1c is approximately 3 months,
Yeah.
you know, and it kind of, it's really only tracking the last 3 months. How long is this pace of aging tracking?
Yeah, so the pace of aging is actually can be changed very, very quickly. We've seen significant results in our trials even at 4 weeks. And so we actually created a lower price point test just to do the pace of aging and telomere length because that can change relatively quickly. But for most of what we
Mm.
do and the big algorithms we really like, we wouldn't necessarily recommend it more than every 6 months. We want to make sure that whenever we see change in your metric, it's true biological change that's informing you about what to do or what you're seeing. And sometimes in smaller intervals, we might not see that same resolution. So generally, we say test, once every 6 months to once every year to get a good idea of where you're going. And then if you really want to implement even more strategies or see what, with personally working for you, where you could have that Dunedin pace is rapidly changing and one that we recommend to look at.
Oh, interesting. So that changes within 4 weeks.
Yeah, very quickly.
And
And yeah.
yeah. And so what was like, let's say, I also know that the younger you are, the lower your pace of aging is going to be. Is that correct?
Yeah, it tends to
So
increase with age.
yeah. So let's say for um, so how do you know? Like you kind of want to equalize it. Somebody who's one age is say, oh, my pace of aging is point 0.6, whatever, and somebody else is like 90 years old and
Yeah.
they're point 0.8. But like, how would you compare that?
Yeah, so generally the way that we keep it, I should say first off on the reporting, we don't most of the time. And the reason for that is because no matter where you are in your pace of aging, it's predictive. So for instance, even if you're at 1.01, just slightly above one, no matter if you're 20 or you're 80, the same risk is going to happen to you based on that absolute rate of aging. So you have a 56% increased risk of death if you're above one, and you have a 54% increased risk of a chronic disease diagnosis. And that no matter what your age is. However, if we really want to standardize this to see, what or how good are you for your age, and we do this actually on. We created a website called Rejuvenation Olympics. It's a leaderboard for people on this testing to see who's doing the best and who's having the best reversals. And when we try and standardize that as a relationship to age, we do this based on what is your predicted Dunedin pace for a certain age. So we actually use our that sort of that trend line that you're seeing right now. And then we basically say how far away from that trend line are you for your age group? And so
Right. So
the
here, so
intrinsic and
this is the trend
yeah,
line. This is where where you should be, and then let's say this is where I am. So it's like
correct.
you look at the trend line for where you should be.
Yeah. And you can see it
Okay.
goes up over time. I would also mention that in a regular normal patient population, you'd probably see this average blue line be a lot higher, quite frankly,
Oh, so this
where
is in your population. This blue line.
this is our population, not I would say
Oh,
a
okay.
normal
All right, that's
population.
important to that's
Yeah.
important to know because I'm
Yeah,
like,
it
okay,
it
I'm
means
pretty good. It actually
no,
means
but
I'm better
yeah.
because this is among
Mhm.
people who are pretty healthy already.
Oh, exactly. Some of the healthiest people in the world, quite frankly. And so yeah, so if we look at here, right around 50 years of age, the average pace of aging for us is still a good bit below one. Whereas in that Dunedin pace cohort, which created this algorithm, the average at 50 was around one. And so
Oh,
we're seeing,
wow.
average differences around, 0.12 ish from more normal patient population. And so, yes, that's one thing. The first thing I usually tell people as we review the results is don't be too hard on yourself when you look at the population because you're competing with some of the healthiest people in the
You competing with me, I'm taking like
world.
150 supplements a day.
Exactly.
Um,
Exactly.
well, what? How much? So I was trying to estimate like every year is point what change in terms of
To be
like if
honest
I'm
with you,
trying to
yeah,
compare it to somebody who's older or younger, like I want to make that calculation. Okay, you're 50, so you're going to be point 0.5 higher than me or whatever, right?
yeah, yeah, definitely. To be honest with you, I don't know the trend line of that slope, that y equals mx plus b formula, but I can get it for you. I can tell you what that average slope is, so you could even just plug in the
Okay.
difference in years and calculate what that average increase is going to be.
Yeah, and I feel like on that, Rejuvenation Olympic site, it should actually take that into account
We do.
probably. Be
We
Oh,
do.
you do?
Yeah, we
Okay.
do. We use that trend line, and say, what is your Dunedin pace versus your predicted Dunedin pace for your age?
Oh, okay, I got it. Oh, okay.
Yeah.
So it's the difference that is what makes you,
Correct.
leaderboard
We
or
were
not.
yeah, so again, we want to absolutely none of these things can actually go too low. The lower you are, the better in almost all of them. But as we're if we had a leaderboard of Dunedin pace, and we didn't segment by age, then everyone on the leaderboard would be 18 years of age,
Right.
right? And so that's not very helpful for anyone. And so we do factor this into account by talking about that trend line and what your predicted age would be versus your actual age. And so that's the way we standardize
Right.
it and make sure that we don't just have 18-year-olds on the leaderboard.
So these can change pretty dramatically within 4 weeks. That means that you really do need to, like, take it a few times in order to see really what your value is, right?
Yeah, yeah, they tend to be pretty consistent. There are a few things we know which can cause pretty massive changes in this. One is pregnancy.
Mhm.
Pregnancy will have women's rate of aging go pretty high, up to the 1.3s,
Oh,
generally.
wow.
Yeah, same with even recent surgery. If you've gone under surgery and anesthesia, we see elevations for about 2 weeks, until after stopping surgery. And then
What
another
if you
really
had
well
COVID or
yeah,
the
that was
flu
my
or
next one.
whatever?
That was my next
Okay.
one. So COVID also increases this rate of aging for about 2 weeks before normalizing back to
Okay.
where you were previously. And so all that to say that, if you're doing a test and you're worried, "Hey, I had this major event in the past couple of weeks," just wait maybe 2 weeks, and then it should normalize. And you can always test again. But yeah, there are some factors which will cause that transiently to increase, just basically high periods of stress, or stress on your body.
Okay. So what was, like, the best score you've ever seen here?
So I've seen I think a 0.58 here before. But even on the rejuvenation Olympics, we make it a mandatory rule to have at least 3 tests over a minimum of 6 months. And we say
Okay.
that so that people can't game the system. We want this
Mhm.
leaderboard to be real and actionable, and also provide us really good data. And so I think currently the best average, on that rejuvenation leaderboard, I think is 0.71. And so, if you were to perform, like this on your next 2 tests, you would probably be in the top 5 of that leaderboard.
Okay. That's nice. And where's Brian Johnson, on that leaderboard?
Yeah, so I think that he's 6th overall. He's the number 1 in relative change. So he
Mm.
started with a rate of aging of 1.01 and then was able to reverse that to
Oh,
0.69.
wow.
Yeah, so he
Wow.
went down significantly in his rate of
Thing
aging.
is that
Um,
I didn't get a chance to do this test before I started
yeah.
taking 150.
Yeah, you didn't have a good baseline to see what's working. But yeah, so and actually we're actually about to do another Rejuvenation Olympics update tomorrow. And on the new leaderboard, actually 5 people have beat Brian in terms of the relative change. And so we actually have somebody that went from 1.2 to 0.89. And so another
Okay.
pretty big change there. We have so
But
we're
I feel like the difference is not. I mean, it's a useful metric, but at the end of the day, I feel like a lot of people doing this test, me included,
yeah.
have already been doing things for a while. So I basically have to, like, just stop everything, not
Well, that's
exercise, like, take the test. Oh, and then,
well, so that's why we have 2 leaderboards. One is the
right.
biggest change, biggest improvement, and then the other one is the best overall result. And so that way, we don't have people gaming the system, making, smoking, 10 packs a day for a couple weeks to get their first metric, and then, stopping and then, trying to improve their health and having the best score. So we do have 2 leaderboards, for that reason.
I want to go into some of the things that can improve this, but before we do, I don't. I doubt you're going to know the answer to this, but have you done any research on thyroid hormones and the Duden pace value?
So we haven't, so in our newer algorithms, the omic age algorithm I mentioned, we do include thyroid measurements, but it didn't register as significant. And in this pace of aging, that was not included.
Okay, that's
Yeah.
interesting. Um, the what about, even was that including free T3? Because free T3 actually shows some good predictive value in terms of
Yeah.
like reducing mortality.
Yeah. So yes, we did include hormone levels in our Harvard omic age cohort. And although testosterone actually was not selected, but one of the precursors of testosterone, androsterone, was included, which also drops with
Oh,
age, which
interesting.
also So we know that hormone loss with age is a driving factor of aging biology. It's why we selected some of it, but that was selected over testosterone in particular, or even free testosterone. But we also
You
had other
said
things
that's
like
androstenedione or did I
androsterone, yeah, sulfates.
that's different than androstenedione. Okay.
Correct, yeah,
Okay.
and, but it's just one of those precursors, and so we did see it as relevant, when we included in that model, everything you could possibly imagine. We didn't just include, testosterone and free testosterone, we also included sex hormone binding globulin,
Mhm.
IGF-1 binding globulin 2, IGF-1, binding protein 3. We measured over, it's 28,000 peptides and proteins. We measured over 3,200 metabolites, including most of those, including neurotransmitters and gut microbiome metabolites, the whole nine yards to see what was selected out. And we ended up collecting 36 different variables that were included into our final algorithm. So we did take a lot of that into account into our newest algorithm, but not everything was selected as the most predictive or important.
Okay. Now let's talk a little bit before we get into what we can do to lower our pace of aging. Let's get into uh, a little bit what this extrinsic age. I feel like it's
Yeah.
not the best title. It's like
Yeah.
really your immune system age, right?
Yeah, certainly. Immune system age is the best way to describe it. And I do hate to mention that both of those intrinsic and extrinsic ages will be removed from our platform next week and replaced with this new omic age that we're talking about. Because as you
Okay.
mentioned, this is a this the naming and convention here is a little outdated and quite frankly a little confusing. And we did it to maintain scientific accuracy, but now there are
Hmm.
better methods, and so we're going to be updating. But you're right. This is basically immune age, and this goes back to that problem I was talking about immune cell subsets and how someone has a change in one immune cell, it can drastically change their epigenetic aging. And so on that intrinsic age, we control for immune cells so that your change in immune cells is not going to impact your age. That's why we call that intrinsic age sort of your
Hmm.
body's age. Whereas with this extrinsic age, we don't control for immune cell subsets. And so,
Okay.
so it's really measuring how your immune system is doing rather than just how your overall body is doing.
So
And
let's just go through that a little bit. How is my immune system doing? I mean, it looks good
excellent.
from
Yeah.
the look of it, but I have no idea.
Yeah, so a couple things to note here is that for most people, we would expect their extrinsic age to be around 8 years younger than their intrinsic, is what we typically
Okay.
see. But for
Among a
you,
healthy
look.
population.
Correct, correct, and if you look at yours, there's another thing on that population level graph, you're way below that midline, which is a good thing, but it's especially good because you're a man. Men age worse than women across the board. In our new reports, we actually have this population level graph separated into men and women, so you can have a better comparison because women just age much, much better. So you're doing well, period, for the entire population, but you're also doing extremely well for a male in this population. And so that puts you probably in the top 10% of people your age for this particular immune score. The other thing, though, we like to look at here is because we can read out your immune percentages. If you look at your CD, we like to also look at the CD4 to CD8 T cell ratio.
If I took a
And
blood test, this is exactly what I would get, or this is just a prediction of what I would get?
it's a prediction, but it's a prediction that has the same accuracy as flow cytometry. We have less than a 0.3% error versus
Oh,
classical
okay,
flow
so it's just as
cytometry.
good as a blood test. Got it.
Yeah, we just published that in Genome Medicine with Harvard and Johns Hopkins. But yeah, we can quantify immune cell percentages with the same accuracy as flow cytometry, and that's a $6 billion industry. They need a lot of blood and they need it refrigerated, whereas we
Mhm.
just need a drop and can have the same resolution. We can't give you your absolute cell counts, so we can't tell you how much of
Mm.
how much total, but we can tell you the relative percentage by looking at unique signatures in that epigenome that are different among each cell type. So again, as your cells go from pluripotent stem cells to these different immune cells, they each do so by having expression of different epigenetic signatures, different on or off switches. And so we can look in this, we can look at this entire thing to be able to see what percentage of what cell type you have with really high resolution. And so for you, we also culminate this in the CD4 to CD8. We want this to be between 1 and 4. And as we get older, this tends to drop, and this is the reason we have this immunosenescence process. It's why people who are older get vaccines first because their immune system slowly degrades over time. And they are less able to mount a response. But where you're at here is exactly where we want. We'd be usually for most people, they're between 1 and 2.5, and you're exactly where we would want you to be. So based on your immune aging, your extrinsic age, and that CD4 subset, you look like your immune system is aging very, very well.
Okay. That's good to know. And okay, so that's this. Now let's talk about how do we reduce the pace of aging. Let's
Yeah.
you could bring up some slides or whatever you want to do, or you could
Yeah,
just talk
happy
through
to.
it.
Yeah, I'd love to bring
Okay.
up just a few slides if you don't mind, because there are two ways that we talk about interventions here, and I want to describe both of them. The first one that we always try and share to people is again talking about publication, talking about validation. We also like to share this. So if anyone needs this, they can always reach out to me. But this is a full list of every interventional trial that's ever been done on biological aging.
Oh,
So
great.
this looks at a baseline measurement. So people take a baseline, they start a procedure, and then they measure again to look at the outcome of that. And so we've got a lot of data here, but I hate to say it, a lot of the things that you'll see here are relatively intuitive, things that you probably should know or be doing already.
Right.
Um, so a lot of this is not groundbreaking, but now we're actually starting to get to really unique recommendations and procedures. So I can always send this, and again, the things you see here are making sure you're eating a non-processed food diet. Mediterranean diets are very, very popular and work very well. We see, don't do bad behaviors, right? So that means you should exercise, you shouldn't smoke, you shouldn't drink, you should reduce stress as much as possible. Stress is surprisingly a major impact on some of these markers. Not to get consistent and effective sleep. And for the sleep data, it's actually really interesting. It's not the total amount of time you sleep or even the separation between REM and deep sleep. It's the lack of insomnia symptoms that actually is the biggest driver of
Oh,
this. So,
interesting.
yeah, so making sure that it doesn't necessarily matter how many hours you get, but making sure that it's consistent and high quality sleep is the way to go. And then again, here you can see that folic acid and vitamin B12 study I mentioned for MTHFR patients, particularly those women who have an MTHFR 677cc variant. Um, but really, these again, this data set's
And is
always
that
growing.
methylfolate they gave or folic acid?
That was just folic acid, but we see the same with methylfolate as well, and it tends to be,
And
any
does
even
it not help
dimethylglycine.
guys, the methylfolate?
It doesn't.
Doesn't yeah.
Generally, it might have been a limitation of the study that they didn't dose it in high enough quantities for men. But we didn't see an effect right here. And we're also doing
Okay.
again other things now. We're looking at hyperbaric. We're looking at stem cells, exosomes. We're looking at senolytic strategies. We're looking at a whole host of different things, and we'll be able to report on these very soon. So this is growing. For instance, our
Okay,
beaver
so
study.
let's yeah, so
Yeah,
let's look at the things that are kind of studied, and then we could go to some of the ththings that are not studied,
yeah.
but you
Well,
might see a correlation in your population if you could share that or no?
yeah, certainly. And so this is the other to answer your, I mean, it's a good segue here because what this PowerPoint does is sort of summarizes all of the cross-sectional data that we might see. So this is basically what are the trends if we look at multiple different cohorts. What are the trends we see for better or worse aging? And again, can sometimes be pretty intuitive, right? So if we look at some of the things that have driven these algorithms in the past, we can look at the big impacts of smoking, depression, and lung function measurements, right? So like VO2 max, as we've already talked about. If we look at even some of these, and I'll try and make it a little bit bigger so everyone
But
can see.
in that one, you're saying, you see smoking actually had a bigger effect than VO2 max.
Oh yeah, definitely. Smoking is huge because some of the
Right.
epigenetic changes that happen with smoking are irreversible. So,
Uh-huh.
for instance, we can tell you how much if you're a current former never smoker, based on changes that will never revert in your genome, based on some of those behaviors.
Even if you
So
smoked how much? Like, I probably smoked, like, 20 packs in my life.
yeah, so probably not there. That's probably equivalent to some of the pollution markers we get, or even secondhand smoke
Okay.
markers that we get. But smoking obviously plays a major impact, and again here you can sort of see some of these other factors and their directionalities. You can see, we have associations with BMI, alcohol usage. We see physical activity being protective. And so we're seeing a lot of these different things. I also, if you don't mind, would love to bring up one more thing, which is from but I can send this PowerPoint. We can talk about some of the things. I also have probably a list of about 7 recommendations that work for everyone. So I'd love to give those 7 recommendations that generally work for everyone.
Let's quickly go through the 7. I bet they're gonna be like, don't
Yeah.
smoke, sleep well,
Yeah.
exercise, eat
Exactly. So
well,
all of those
eat veg
lifestyle
fruits and
things.
vegetables.
Yeah, all those lifestyle things for certain.
Don't
But I
be
also
overweight. Yeah.
yeah. Yeah, so generally, there are a couple things that everyone can do to change and have improvement. One is caloric restriction. I already talked about this, but caloric restriction does work to reverse these epigenetic age biomarkers. So
Give us
yeah,
a magnitude of like, okay, so let's say
yeah.
do 10% caloric restriction. What kind of change can I expect?
Yeah, so 10% caloric restriction will probably reverse your epigenetic pace of aging over the course of. We did our study over the course of with there was the calorie study actually done by Daniel Belsky from Columbia, published in Nature about I guess now 7 months ago. Showed that on average that you can reverse your Dunedin pace by around 0.12 over the course of a year by just doing 10% caloric restriction.
Oh, that's a lot.
Yeah, yeah,
0.12
definitely.
is significant. So
Yeah.
I wasn't doing caloric restriction. So let's say for me, for example, I could go from 0.72 to zero point 0.6, let's say, if I did
Yeah,
10% caloric restriction. Theoretically.
correct, yeah, and so that could help, but, for someone who's already pretty good on that rate of aging, you're probably not gonna see the same benefits as someone who's not. But caloric restriction and also things that work, caloric restriction, it's been hypothesized to work by inhibiting mTOR. This really good, mechanism for longevity. So we also like other things that work on that enzyme, like rapamycin, for instance, methionine restriction. All of those tend to have positive impacts. So I would put all of
Okay,
those 3. Yeah.
quick question. What on the list do you not do of the things that
So
improve it?
yeah.
If you don't mind sharing, we
Yeah,
could
no, I'm an open book. I'm happy to share,
okay,
but
of
I also tend to switch things up a little bit. I use myself as a
course.
way to learn a little bit. But the biggest thing for me, and I joke about this a lot because I was one person who did not believe in meditation or mindfulness or stress exercise. I always used to think, am I doing this right? When I'm sitting there or
Same as
those type of
me.
things. Yeah, and so it was really hard for me to say I like this as an intervention, but I've done the biggest reversal in how I treat mindfulness, meditation, stress reduction. There have been multiple studies that show even your ability to control your emotions are highly predictive of your epigenetic aging. So if there's one big reversal thing that I've done, it is I started to do hot yoga as a way to spend some time doing some mindfulness and meditation and definitively it's reversed my epigenetic aging. And I see this across the board. Stress
What
is a
kind of
big
magnitude
mover.
did you see?
Yeah, basically that big improvement in my biological age from baseline,
Was
around
mainly
3
from
years
that.
older.
So, like, not
I would say, yeah, but I also, a big believer in some supplements like vitamin D, DHEA, alpha ketoglutarate. Those have been shown to have some pretty positive effects. Metformin has been shown to have positive effects. In addition to
DHEA
that,
what do you, like, look at your numbers before you supplement with DHEA?
so I didn't. And in the cohorts we've looked at, mainly it's been a cross-sectional analysis. So the answer is we haven't really quantified where someone should be versus where they are. But we do know that DHEA has tended to be positive. Omega 3s are generally positive. So a lot of these supplements that are relatively common are tend to be pretty positive. But I would say that definitely one of the surprises is lithium supplementation at 10
I take
milligrams.
that.
Yeah, it tends to be
10
really good.
milligrams? Okay.
10 milligrams, yeah, so a small dose, right?
I take 5 milligrams.
5 milligrams, that's good as well, yeah, but and then so those have been some surprises. We also, in our new Omega Age, identified 2 other supplements, which tend to be protective, and that's uridine. That's a product that generally
I
increases
take that.
mental function. I'm surprised. That one's a rare one. And then another one is carotene-diol. It also goes under the name lutein.
Oh, I
And,
take that too.
yeah, generally used for eye function, but, we've seen these carotenoids, tend to be very protective in that process as well.
I'm surprised that uridine had a big effect.
Yeah, definitely. It's a really not well talked about, but there are multiple studies on aging showing that you can reverse intestinal aging. And that's actually one of the major metabolites, which is increased in recovery and repair in a lot of animals and stem cell activation, but especially salamanders as they're regrowing, tails and things. Uridine is a pretty important metabolite.
And so the DHEA, just to go back, 'cause DHEA is in my list of, like, I don't know if I should keep it or take it out. I kind of wanna I actually put it in because my DHEA was low in the beginning, but then I read that thyroid hormones, can increase DHEA and pregnenolone, and so I thought maybe like I'm increasing my thyroid hormone levels naturally with like
Mhm.
herbs and stuff, and so I'm trying to see if that's going to increase my DHEA.
Yeah.
But what like I'm trying to understand how you how you work with that. You don't because you're not testing for it. You're just taking it because it should is it the higher levels the better? I feel like it should be in a range.
Yeah, so you're exactly right, which is why we've developed, this, and this is our new omic gauge, and this is what I mentioned. The testing that you received from us, you didn't get the why, right? You didn't tell about what was driving your aging process, but now we can actually read out these individual markers. So, for instance, I can tell you out of all the clinical values that we predict, what is increasing your aging versus what is decreasing your aging.
Oh,
And I can do the same with proteins, and I can do the same with metabolites. And so what we can start to do
oh.
is start to quantify which system in your body might be having the worst versus best aging, but then also
So I'll
make
get this on my
recommendations.
next test.
Yeah, so you'll get this, and then, for
Oh,
instance, we'll
awesome.
actually even read out to you these factors. So we'll actually be able to tell you where your hemoglobin is, your creatinine, your hematocrit, and where you stand in that population. And this is just for the clinical values. We also do it for these metabolites. So here's uridine, for instance. We'd actually quantify your relative level to see if it's even something you need to consider from a supplementation perspective, or we
Ooh.
can do it with carotene, or in plasmalogens, which is something common lately. We can do it with a variety of things like cysteine, or again, here's your androsterone sulfate as a factor, which was included. And so we can tell you about a lot of these and the processes which they're implicating. So now we can give you a little bit more of the why, to make personalized recommendations to really stop, that aging process as much as possible.
Okay, so, albumin, let's see, it's point 0.1, it's not I
Yeah,
guess
well, albumin
and
is actually one of the highest weighted out of all of these.
okay.
And so here you can see, so these are the factors here which are associated with improvements in omic age, and albumin is the highest weighted. Albumin seems to be very, very important,
So,
because it's able to
what does that
bind
mean, though?
it.
If it's higher,
Yeah.
it's
So
if
the
it's
higher,
lower, it's
yeah,
yeah, go for it.
so the higher the albumin, the better, essentially.
Right.
And albumin tends to decrease with age. And albumin itself is predictive of mortality, just as a standalone feature.
Right.
But with that being said, here you can HbA1c. This is a negative thing. You want your HbA1c to be lower. You want your creatinine to be lower. You want your blood urea nitrogen to be lower. Whereas you want your hematocrit, your hemoglobin, and your
It's
albumin to be
interesting.
higher. Yeah,
I
you want
wait,
your
wait, heme
your
that's
same.
a little okay, so I've actually done research on all these biomarkers. I'm
Yeah,
talking to someone who's looked at the research and all this stuff, and I would say that the research for albumin, HbA1c, the research also, shows higher albumin, the better. I would say, for all these, it's accurate, although I wonder why triglyceride doesn't seem to have any effect.
it's a
Um,
very small effect size. Yeah,
yeah, but I would say the 2 that are different than what you would see in the research. You know what? Okay, so hemoglobin, if it's too low, it's a big problem, huge problem, right?
mhm,
Because you're not getting oxygen to all your cells. That I wonder if it's but if it's too high,
it's also
it
a problem.
actually
Yeah.
increases cardiovascular disease because it thickens the blood.
Correct, and there are
Same with
byproducts.
hematocrit.
Yeah, and so some of these things are not linear, I should also
Mm,
mention,
okay, that's
right?
what I wanted to ask. Yeah.
Yeah, and the crux of everything, every biomarker is that generally there's probably going to be, a level that's too high and a level that's too low, right? So these are not always linear, and in new approaches to these algorithms, this will only get better. But yes, so in the future, we'll be able to tell you, I would say about 60 to 70% of what you get on your current lab testing, all with just methylation as an output. And some things we can predict very well, others we can't at all. So for instance, that triglycerides, one of the reasons that our triglycerides is so lowly weighted is because our prediction model is not very good for triglycerides, with DNA
Mhm.
methylation. We're not very accurate in our prediction for triglycerides. And whereas we can be very accurate for our lung function things like FEV1 or VO2 max, for instance. And so some processes don't always are not always manifested in methylation. And in those cases, generally they might not be represented, but those tend to be few and far between. Triglycerides is one, but senescence is another one that we really haven't figured out a signature for.
Interesting. So let's see, let's go down a little bit. Let's just see
Yeah.
some of the other. So I like all those blood tests. I mean, that actually goes really well with the lab analyzer because you can actually upload it. It'll tell you what your optimal range is for each of them and how to
E
optimize those.
exactly, and so, yeah, Joe, you're right up my line of thinking, and that's why I think we love your platform so much, because, these are just the 36 that were selected for this aging algorithm, but we can do,
Right.
everything from your alpha-ketoglutarate and your spermidine levels to your vitamin D, your vitamin C, your vitamin E. We can quantify
Oh
all of those
wow,
with just DNA
spermidine is
methylation alone.
nice. Yeah, because
Yeah,
you're not
yeah.
going to really take a blood test for that.
Yeah, exactly. We can do ergothioneine, we can do your ketone
Oh,
metabolites, we can do
I
your
take ergothioneine.
yeah, so we can do a lot here, that I think would be a really good fit with your platform and report.
So cysteine, is that you want to get that
Yeah, so
lower or high?
cysteine is so this is one of the surprises. Cysteine was actually shown, to be a negative influence. You want lower cysteine, which was, most people think of supplementing even cysteine or cystine as a way to be an almost like a anti-toxicity type of product to
Right.
increase your glutathione and things of that nature. But we actually saw a negative weight here, which is it gives us some questions, but it might be to, that things we want to convert away from cysteine into these other markers a little bit better. And so some of these
Right.
require, some more thorough
But also, I
investigation.
wonder if this cysteine is different than the other cysteine that
Yeah,
you're taking N-acetylcysteine, which is like, or
yeah.
somebody would be, right?
That's
Not, no,
different.
not
Yeah,
taking.
slightly different though. It's slightly different than what we're measuring here, I should say. But yeah, most people will be taking, the N-acetylcysteine, or they might just be taking the cysteine as it's more bioavailable. But so yeah, so there are some questions here as well because some of these things, you take ribitol for instance. Ribitol is the only thing that's weighted higher than albumin, and there are about 2 studies published on ribitol. And so we don't know why this was included so much. Generally, the studies that have been
What is
selected on,
like? Can you
yeah,
ingest Ribidol
you
or
can. So it's part of, I should say, several pathways in your body, but particularly, some, I would think some glycolysis related pathways and energy production pathways. And so, but again, if you were to search ribitol, you'd find almost nothing about it, clinically. And so we don't know why it was selected, but the weight is higher than anything. And so we had to include it. The only other paper out there that has ribitol in it is a paper which did a very similar approach, which basically asked which of these metabolites are predictive of longevity, and it selected ribitol as well.
interesting? Okay. Quick question for you. How many supplements do you take a day?
A lot. I'm not quite like Brian and over 100, but I'll probably, I think, I tend to be worried about even mixing, because you might have different effects as you mix, but I'll still take, I would say, about 14 to 15.
Okay, interesting. And
Yeah.
and which ones are you taking because it's lowering your methylation age or
Yeah, alpha
pace of aging?
ketoglutarate. Yeah, alpha
Okay.
ketoglutarate, vitamin D. I do like, vitamin K2 and E. I like, and again,
Vitamin
this is just for.
K2 will help pace of aging?
Oh, so this is just for me. This is all N of one single, anecdotal study, not a meta-analysis, not something I would tell everyone to go out and take. But vitamin D is one of those that has multiple studies.
Right.
Alpha ketoglutarate doesn't really have any good studies in methylation aid, but I'm a believer in it for all the other studies that exist on it. Omega-3 fatty acids, I'm a believer in. I will take sulforaphane. I'm a big fan of that one. So I think that those lithium, as I already mentioned, uridine, now carotene those are on my list. I think a couple other from more performance related things, which sometimes might conflict with biological aging, but I think you sometimes need to maximize quality of life and
Right.
overall life. So there's a lot there, but hopefully that's a good start.
What do
Again,
you take, like, testosterone replacement or
yeah, certainly started that actually just relatively recently. But in addition to that, I'll do I have a couple other sort of branded products that I like that I won't necessarily do a shout out on, but things for I'm a big fan of nitric oxide and vasodilation and blood flow. So there's a couple things I take there. Also, my background's in peptides, so a big peptide user as well.
Oh, interesting. Okay. I've never really like I've taken peptides, of course, but never got big into it. No clinical trials.
Yeah, I've got a database with about 60,000 clinical peptide trials. If you ever want to look,
Seriously?
yeah, I've got probably more data on peptides. I can send you the folder if you ever want to go through any in
What
particular.
tell me, okay, let's I guess we'll go a little off track, but what kind of peptides do you take? With
Yeah, I could probably spend all day talking about this, but I'll
well,
just
like,
maybe
what do
pull
you
out.
take? You're how many
Yeah,
are you taking? Like,
so I'll
you're not
probably,
taking
I'll probably take 2 or 3,
okay,
on at any one time. But my
at any one
one of
time.
my favorite is the SS31, the mitochondrial peptide that, and this is not hyperbole. This is a direct quote from a clinical trial. But one injection of this product, SS31, is the equivalent in ATP of 6 months of daily endurance training exercise.
Wow.
And so big fan of that one. It helps in just about every condition because you're just increasing and improving your mitochondria, and your mitochondria are needed for everything you do, right?
And how do you
big
get
fan of
it?
that.
How does somebody get
I'll have to, though. Unfortunately, the regulatory routes for some of these things have closed. There are still pharmacies who do it, but I won't make any recommendations beyond go to your physician and see if you can find it.
right, okay.
Mm,
But
yeah,
there are physicians that can order it?
there are, yeah, certainly,
Okay, interesting.
yeah,
And so what else? Oh, interest like, that's very
yeah.
okay, what else do you take?
So
New world for me, I guess I
yeah.
don't know a lot about it, yeah.
Yeah, so I don't necessarily wanna be too controversial on a lot of these things, but, I am not diabetic or pre-diabetic, I also like, some of these things like GLP-1s, these peptides like semaglutide,
Oh,
people know them as
interesting.
these weight loss drugs. I think that they have some longevity benefits, and having a optimized HbA1c and fasting insulin for me is very important. So I will take that, it's sort of a relatively lower doses than what most people would be using, but I'm a big proponent of them as well.
What's your HbA1c like now?
Yeah, so my HbA1c is around 4.8, and so it's pretty good. But I want to keep it as optimal as possible.
Okay, interesting. So you wanna keep it, like, below 5?
Yeah, yeah, certainly.
For
Um,
anti-aging purposes.
Yeah, there's some other, I would say medications I really like in that area. The SGLT2 inhibitors like, canagliflozin or empagliflozin. Those help you basically pee out your glucose. They make your kidneys permeable, that I really like. They've been studied in the ITP trials on mice as one of the very few things to extend lifespan, but also have some other benefits, such as increasing, some of short chain fatty acids in the gut and some other things. I'll do a lot of things to experiment, but there again, I don't think that, much like we talked about with Brian Johnson, you don't necessarily need to spend $2 million to have improvements in biological age. You can do even simple and easy things. And so I don't want to
Did
overwhelm
you
people with what I do, whenever they can
No,
do their
100%.
own
This is,
things.
like,
Yeah.
kind of the bonus. I think we went
Yeah.
through the main things I wanted to go through. This is more like the bonus part of the
Yeah.
episode. But when you took SS31, did you feel like, "Whoa."
I didn't. And to be honest with you, one of the things about SS31 is it has better effects the older you are. Because what it's really correcting so our mitochondria has two membranes, one outer membrane, and then everyone's seen that curved inner membrane that looks just wavy. And as we get older, much like a t-shirt you wash too many times, where the neck slowly separates and gets loose, the thing with that inner mitochondrial membrane is that those curved structures slowly start to get further and further away. And when they do, those electron transport chains become less efficient because it has to take all of these things so much further, even just in space. And so what the SS31 does is it takes those loose mitochondrial membranes and makes them really tight again. And that pushes that electron transport chain so close together and makes energy production even more optimized. And so for me, I was probably a little too young to feel anything, but I've seen it work in so many other people. And I'm such a believer of the mechanism. Having optimal mitochondria is so important for everything that we do.
Okay, I feel like I need to learn more about this whole peptide industry
Yeah.
because I always felt like you I wanted to go with things that were more fundamental first, and I felt
I
like,
think
okay, so first I optimize my diet, my lifestyle. Then, I've been in a long supplement phase of trying to optimize that, and that's like a massive field because there's like thousands of supplements on the market. So
yeah.
me trying every one, mega dosing every one, looking at all the mechanisms and how they're working and what's going on. Um, like that takes a while, right? I've done like 4 mega dosing experiments
Yeah.
in uridine. I've been taking it on and off for a number of years. I mean, I started taking that like uh 12 years ago.
Yeah. Yeah,
So,
definitely.
yeah, I mean, but okay, so but let's and I just felt like yeah, like the peptides I wanted to save like okay, once I'm done with all the things that are like more fundamental like nutrients,
Yeah. I think
I
that's a
discovered a lot of nutrients and
yeah.
amino acids that I needed more of
Yeah, and
or you know and yeah.
yeah, I think your approach is certainly a good one. Right? Because one of the things also about the peptides is traditionally in the past they have very short mechanisms of half life, and so oftentimes from a cost efficacy perspective, the peptides may be the last thing you want to add because they're probably the most expensive for sometimes marginal benefit. But
Right.
there are always exceptions to that rule, and especially as these peptides get better in terms of class. So, but I think your approach is certainly the right one, especially because there's so much more data, as you mentioned on nutrition, and optimal nutrition rather than some of these peptides, which are very, very new.
Yeah, and I think people can take away like, you know, if you're not doing the basics, if you're smoking, if you're not exercising every day and diversifying your exercise, if you're not if you don't have a good diet, forget about supplements, forget about everything else. You know, it's like that's already, you know, I would put like a hierarchy. You know, there's like, okay, diet, lifestyle, top, right? Then you have supplements. Then you would have uh maybe certain pharmaceuticals that would
Mhm.
really help you. And then you might go with certain peptides that are more novel once you like really exhausted all the other avenues. But I wanted to talk about two things, and then we'll end it there. Metformin and rapamycin. So those were two things that heard somewhere that you found lowered the pace of aging. Is that true or not true?
So, yeah, I should mention that studies on both have not yet been created. There's about to be though a study which shows metformin reverses all of the epigenetic age clock, and that's going to be coming out of Cornell. So I think
Mhm.
that it's safe to say that yes, and that was not in diabetic populations. That was in patients that didn't have diabetes as a mechanism that was a particularly a big issue. So I think that's important. On rapamycin, I can tell you that in our cross-sectional analysis, we certainly see benefit, but again, no study has been published. And we are doing a controlled study right now where we're taking, naive patients, putting them on rapamycin and then looking at outcomes, but we haven't analyzed that data yet. So whenever
Right,
I
it
say
could be
rapamycin,
the people
yeah,
who are taking rapamycin are just the most hardcore people like Brian Johnson
exactly.
and me and
Yep.
you wear
And
whatever,
me.
right? And
Yeah. And so
I was
so
about to ask you, I'm
yeah.
like,
And so yeah, so I think it's still early. Metformin, I can say very confidently probably has some positive effects on these biological aging clocks.
"Do you take
And I can also
metformin?"
I don't, and only because I'm on the GLP-1s and the SGLT2 inhibitors, which are having, I would say, an anti-diabetic effect already. And some of the side effects of metformin, I don't agree with me. And so
Ugh.
for
The
that reason, I
mitochondrial stuff or the gut?
GI stuff, yeah, more so than
GI.
anything. And so I
The slow
tend to,
release as well?
yeah, definitely. And so I tend to favor other medications in that same area. Like I said, the GLP-1s, the
Of course.
SGLTs. But again, I think I certainly see the benefit of metformin. So
What
with
about
that being said,
acarbose?
yeah, a carbo. So another good one. Again, just talking about increasing short chain fatty acid in the gut. Another good one. It's one of those other four products from the ITP trials on mice that extended lifespan. I'm a big fan, but again, you have the same sometimes issues with some of those GI side effects. And so I don't do a carbos, although I'm a believer in it.
It gave you GI side effects?
Oh, I didn't take it. I haven't tried the
Okay.
acarbose, but
It gave me GI side effects, but I wanna try it again,
yeah,
under
I'm a
different
big believer again in the mechanism. But again, I being on the SL2s and the GLP-1s probably less important for me.
Awesome. Okay. Thanks so much for coming on, Ryan. I
Yeah,
really learned quite a lot, and maybe one day you'll teach
yeah,
me about peptides more. I'll teach you about supplements more. I
love
mean,
it,
you
love
probably know
it.
a ton about supplements already, but um, yeah, it was
Yeah,
really a pleasure talking, and also hopefully, I think the platforms that we both have are complementary. Like
Mhm.
they're telling you different things. They're both useful on their own right, independently. So I think some collaborations there would be really nice as well.
Yeah, I can't wait to do it. Hopefully, we'll have some updates on another discussion.
Oh, awesome. Okay, so yeah, I'll take another test, and then hopefully we could do another podcast and discuss the results of that omics age test.
Sounds great. Thanks so much, sir. I appreciate you having me on.
And just, I guess we should say, where can people go and buy this test?
Yeah,
uh,
so I recommend going to our website at trudiagnostic.com. That's TRU diagnostic, and diagnostic is singular, no S, .com. And if they have any questions, you can always reach out to me at Ryan at trudiagnostic.com.
all right, awesome.
All
Appreciate
right.
you being on.
Thanks, Jeff. All right. Bye bye.
67% of listeners aren't subscribed to the show, so please don't forget to show your support by hitting the subscribe button now. You'll not only be supporting the show, but also investing in yourself and your health journey, all while helping to keep us ad free.